exactly because they do not match, you need some additional gauge symmetry to get rid of those extra degrees of freedom, or to have some constraint. But that's why when you work with field theory, you will get additional constraints on the fields or additional symmetries. Those ensure that the number of degrees of freedom match the ones that you expect from representation theory of Poincare. But if it is too complicated, don't worry about it. It's not the main topic of this course. We mainly care about classical field theory, calculating Green's functions and trajectories and this sort of things. This discussion is just to what is the goal of this discussion? The goal is to say that it fits in a general framework that connects with what you learn in QED and QFD. You can actually think about all of them as one general framework to describe interactions between particles. Okay. Yes.
My first question is, people don't talk about higher spin fields like spin 3 or 4. Is there any particular reason that we are not discussing them or looking at their properties or whether they exist or not?
Oh, people actually talk about them, but not in the textbooks, because well, first, one reason is that they are more difficult. The theories of higher spin particles or fields are much more hard to construct. They are much more constrained. And there are some qualitative differences as you go to higher spin. So for instance, like in QED, you study these renormalizable theories with, I don't know, just electron and photon. You could do calculations. As you go to higher spins, then you discover that having interacting theories of higher spin particles is much more difficult. You usually need to have a tower of particles with higher spins if you want to go to higher spins. You cannot restrict yourself to a single degree of freedom without having extra stuff. Also in the theory of, so for instance in nature we do see higher spin particles. There will be resonances of QCD. When people do, I don't know, look at the scattering of hadrons or different particles, they will see various resonances with different spins. And those resonances can have higher spins. But yeah, it's true that they usually come in a tower. So we have never seen an isolated spin 3 particle which is weakly interacting and just going by itself. It only shows up in some mess in the middle of some interactions and only together with many other things.
What do you mean by tower of particles?
Oh, what I mean is, well, you have this diagrams of masses and spins of the resonances that show up in some scatterings, like scatterings of pions, for instance. So what do I mean? There is a relation which between, for instance, the angle, the spin, let's call it J and m squared. And what I mean by tower is that they look at these scatterings and they see that this J in terms of m squared, they see it on lines. And you have many of them. That's what I mean by tower. So they, you have just as you don't have an isolated particle. That's what I mean.
And my second question is the diffeomorphism invariance that we discussed for H mu?
Yeah.
Is it the same as the gauge invariance, gauge redundancies?
Yeah. Yeah, it is. It is exactly that.
I thought the gauge invariance was the conservation of the H mu minus, I mean the Einstein tensor in the linearized version. I thought that was the derivative of that is 0. That is the gauge.
Oh no. That is in a sense a consequence of having a gauge invariant theory. But gauge invariance or diffeomorphism invariance, I use them interchangeably. So these two, for me, these are the same thing. So this is diffeomorphism invariance is a particular form of gauge invariance. It's the one that you have for H mu and nu. Gauge invariance, you also had it for A mu in a Maxwell theory. It was a simpler, smaller gauge symmetry. Now in the case of H mu nu, it's a bigger gauge symmetry which is called diff invariance or diffeomorphism invariance. As a consequence of that, you construct a theory for H mu nu that respects that symmetry. For instance, you write an equation of motion that respects that symmetry, and then that equation of motion will be conserved. Or another way of saying it is that if you want to write an interaction H mu nu coupled to something, so say I want to couple this H mu nu to some other object, some other field or operator that has to have two indices. So we can just call it some O mu nu, some general operator with two indices. The fact that the theory has to be invariant on the gauge symmetry, so if this is S interaction, the fact that under some gauge symmetry, gauge transformation S has to be invariant, which means that d mu xi mu plus d mu xi mu times O mu nu, it has to vanish. That implies that this O mu nu has to be some conserved current. And then the candidate that we have for a conserved current is T mu nu, which is conserved. Therefore, the equation of motion for H mu nu that we construct has to also be conserved. Or another way of saying, if you try to construct a quadratic action for H mu nu with two derivatives, which satisfies this gauge symmetry, the equation that you derive from that action automatically has this property that if you hit it by derivative, it will give 0. So it's a consequence of diff invariance. What we did here was kind of the other way around. We first wrote the equation and then constructed the action. We didn't have to do that. Once you have the symmetry, you can just search for the quadratic actions for H mu nu that satisfy that symmetry. And that quadratic action is uniquely fixed. And that reduces to the equation that we wrote. Yes. Other questions? Alright, so today we continue with the spin 2 gravity. Basically we want to understand the phenomenology of the spin 2 gravity at the linearized level. So what we discussed last time was that we want to decouple this. So we have this spin 2 field which is described by h mu nu. We couple it to the energy momentum tensor of matter field. If we have some equation of motion that I'm not going to write now. But it had some interaction which we took to be 1/2 before x times h mu nu t mu nu. But this t mu nu, we take it to the t mu nu of the matter fields. Because we are working on leading order in h mu nu. So we want to work perturbatively in h mu nu. So sometimes I put this index 0 or matter here. 0 means 0th order in h mu nu. But sometimes I don't write it, just to avoid clutter. Okay, so now let's, as before, discuss how this modifies the motion of point particle. Let's try to couple it to the include it in the word line action that we are familiar with. So in order to do that, it's easy. We just need to write the t mu nu of the point particle. And one way to write this t mu nu is to write it as integral d tau x dot mu delta 4 x mu minus x mu. So if I put this there, what the correction that it gives me to the point particle action is integral d tau. But I have the original term that we always have, eta mu nu dx mu d sigma dx mu d sigma 1 minus 1/2 h mu nu times dx mu d sigma dx mu d sigma divided by this thing which is d tau d sigma squared, so minus eta alpha beta dx alpha d sigma dx beta d6. Now one thing that I can do is that as long as I'm working the linear order in this h mu nu, I can absorb it inside this square. So there is a different way of writing it, which is more elegant. Possible order h squared correction. Where this g mu nu, I just defined it to be eta mu nu plus h mu nu. So if we plug this g mu nu to be eta mu nu plus h mu nu in here and expand it to linear order in h mu nu, we will recover that. So for the moment, this is just a notation. I don't necessarily want to give it an interpretation. Okay, now, of course, since this h mu nu is a field, can depend on the space-time, G is also a field. It depends on the space-time. The situation we want to consider is that we have some background h mu nu field, and then there is a point particle that moves in here. We want to see how its motion is affected by the background field. And then the procedure as before, we just vary this action to derive the geodesic equation. Or maybe we never call it geodesic, it's just the equation of motion for the particle, for the point particle. So how does it look like? The equation of motion will be d by d tau of g mu nu dx nu d tau equals 1/2 d mu g alpha beta x dot alpha x dot beta. Again, up to possible order h squared correction. Now, if let's consider, for instance, a non-relativistic particle. Go to the rest frame. Let's assume that we have some field which is time independent, and there is no h0i component. So h0i is equal to 0, and d0 h mu nu is equal to 0. So this is basically a gauge choice. Since we have this diffeomorphism invariance, we can always choose a gauge, or choose those xi mu parameters, so that in the new field will satisfy this equation. So this is always possible with a good choice of the gauge. Is kind of similar to what we do in Maxwell theory, right? You are familiar with these various gauges that we can impose in Maxwell theory, like Lorentz gauge, or what else? Temporal gauge, axial gauge. Here is a similar thing. We can choose the gauge parameter to set these components to 0. So if you imagine this is 0, and also the time derivative of my field is 0, which means that I'm dealing with the static field. Then we can ask how is the motion of a slowly moving particle is affected by this background static field. So what do we get? For the zeroth component of this equation, d0 here vanishes. So I get a constant of motion g0 nu times dx nu d tau is equal to constant. That constant we call it as usual E over m. Also this g0 nu is just g0 0 because remember this g is just eta plus h. But eta 0 I is equal to 0 because eta is diagonal and h0 I is 0 biochar. So this is just g0 0. So what do we get? We get dx0 d tau is equal to E over m. Maybe I'll put a minus here. Yes, so we get this. But just one more. Which is equal to E over m times, now remember we are linearizing in we are linearizing in h, so E over m g0 0 is equal to E over m times 1 plus h0 0. Yes.
In the beginning, we coupled our field with the matter energy tensor, and then here we say that we make it a static, and we let the matter point particle go through it.
Yes.
And we calculate the equation of motion for that. But here we like assumed and neglect the interaction at the same time, right? Because we have already know that matter will affect this our field.
Yes, yeah. So this is the limit of a test particle, right? When we imagine this point particle is a test particle. It doesn't affect the background field by much. It's not a terrible approximation, right? For instance, we have heavy objects. They produce some background field, and we ask how the light objects are moving in the field of these heavy objects.
Yes, but I mean, how we will use this formula for? Because if we want to derive quantum motion for a matter, for the matter in general, how it will interact with the gravity, I think we shouldn't use this limit of derivative equal to 0. Is it that?
This one, well, this derivative is non-zero because the particle is moving. Is that your complaint?
Yes.
Okay, so it's the same thing as we do when we do, like, let's go back to classic.
If we didn't take a test point particle object, we take a real moving object. You know, like for example, if we want to study sun in the Earth system, so
yeah,
in that case or in that situation, we shouldn't use this limit, right?
Yeah, in general, it should include the effect of your whatever you have on the field. Yeah, this is only true when you are considering a test particle. Otherwise, it could still you could still use it, except that it won't be time independent. So you generically will have some masses that are moving. the motion affect the motional part of mass number 1 affects the motion of mass number 2. So unless there is a big difference between the masses like Earth and Sun, so that the motion of Earth doesn't really change much the motion of Sun, unless you are in this approximation, you cannot take the field as static. But already in the case of Earth and Sun that you mentioned, yes, you can essentially take the field of Sun to be static and consider Earth as a test particle moving in the field of Sun.
And we can use this limit also for Mercury planet. Is it the same, or
yeah,
it will be?
Yeah.
So is it like?
I think the only thing that might affect the motion of Sun, well, I mean, it always depends on your precision. At some order, there will be an effect also if you take two masses that are orbiting each other, M and M. Right? What are we saying? I'm saying that you can neglect the effect of the motion of mass M on the big mass M. There will be some effect which has to do with, which is suppressed by powers of M over M. So it depends with what precision you are looking at the system. At some point you will see the back reaction. This is called back reaction. So at some point you will see the effect. But it's like any perturbation theory. You want to you have a small parameter. You want to see what is the answer at zeroth order in that small parameter. Here is the same thing. We have a test particle whose mass is much smaller than the mass of whatever else that you had, which produced the field. You want to see what is the motion at zeroth order in that small parameter, which is mass of this object compared to mass of whatever other object that produced the background field. So what we see is that essentially dx0 d tau is E over m plus some small corrections, and then we can look at the ice component of the equation. And the ice component of the equation tells me that so here I will have di of, let's write d by d tau of g. Now if I look at the ice component, then here there will be gij again because there is no mixed component. Dxj d tau equals 1/2 di of g alpha beta times x dot alpha x dot beta. Now let's make a couple of observations. One is that if the particle is non-relativistic, or we go to the rest frame, then this x dot alpha and x dot beta are dominated by the zeroth component. I remember for a non-relativistic particle, in general, u mu, which was x dot mu, is gamma 1v. So if we go to the rest frame, then x dot mu just becomes 1. So the leading contribution for a non-relativistic particle comes from when alpha and beta are 0. Moreover, we have a derivative of this g. So here we get di of g00, which is of course di of h00, because di of eta 00 will be 0. Eta is just a constant. So the right hand side of this equation is already first order. So to get the acceleration, we can take this part to get a leading contribution to acceleration, we can just take the zeroth order contribution here, which is eta ij, which is delta ij. So the equation in the case of the non-relativistic particle simplifies to theta square. By the way, if it's non-relativistic, then E over M is also 1 from there. So this is really just 1 plus H00.
So when we write the for velocity, we just take the significant term, like 1, but it's actually 1 plus H in this.
Yes, yeah, I'm just taking the zeros order term because I'm going to linearize everything in terms of H. In particular, here you have di of H. So already you have one factor of H, which means that these x dots can be treated as zeros order. And at zeros order, that equation holds.
Left hand side in Gij have also Hij.
Yes, but since the right hand side is already first order, then it implies that this object is already first order. And then I can ignore the thing, ignore the corrections or the H correction to G. That will only give me some order H squared correction to the acceleration. So and then tau and T will be the same, or tau and x0 will be the same. So I can also replace this with d squared xi dt squared, and that is equal to 1/2 di of h00. Now, if you compare this with the Newtonian equation for a massive particle, then we can identify h00 as minus twice the gravitational potential, the Newtonian potential. Once we make this identification, then we can go back and fix that constant that we had in the equation of motion for h mu nu, which relate. Let me remind you. We wrote an equation of motion for h mu nu, which looked like box h mu nu minus d mu d alpha h alpha nu minus d nu d alpha h alpha h mu plus d mu d mu h minus some traces equals some constant times d mu nu. So everything in this equation was fixed except this constant. And this constant, we learned that if we want to write an action for gravity, which we write it as d4x, some kappa over 2 times d mu h alpha beta, d mu h alpha beta, plus some other terms. And then add it to this interaction term, and we require that the variation with respect to h mu nu give me this equation. Then there will be a relation between this kappa and c. Basically, kappa becomes 1 over c. So there is this unknown here, and the unknown will be fixed once we identify h00 with the Newtonian potential, because then we can come to this equation, take the non-relativistic limit of this equation and require that it reproduces the Poisson's equation. So we want it to reproduce Poisson equation, which is So that fixes kappa to be 1 over, I think it fixes it to 1 over 32 pi g. I will not go through the derivation. It can be found in the notes. Any questions so far? So,
in
yes.
this system, the energy of the particle is still the same energy, or to the first linear order of h should we include 1 plus h times the energy? Like in the momentum, we have m times dx0 d tau, which is changed in this picture. So if we want to calculate or measure some particle's energy, if there is an h00, we will measure it differently, or?
Yeah, so it becomes a little bit tricky what is the definition of energy. So you don't necessarily have the so remember how when it is when can we talk about energy? When there is time translation invariance. So here we are talking about the static field, so it seems that we should be able to talk about the concept of energy, some concept of energy. In fact, we already have this constant of motion here. So if there is anything that is a good candidate to be called energy, which is conserved because you have time translation invariance, that must be this constant of motion. It's something that whatever you gave the particle at initially, that remains the same. But yes, so if for instance, now it matters. For instance, if your particle is coming from infinity, then at infinity, and you imagine that at infinity the field vanished, then you will have just the non-relativistic particle with some velocity. So you fix the energy at infinity when h is 0, and then it remains the same. Yes.
In the last expression that we went for the zero component equation of motion,
Yes.
we expanded the 1 over t00 as 1 minus. Then the first one shouldn't have a minus due to the minus of the
Let's see. Did I screw up this time? So what? Let's see this. Right. It was G00, which we can write as H00 plus H00, right? And then. Is it correct? So I write it as E over M eta 00 times 1 plus H00 over eta 00. And then eta 00 is minus 1.
conventions, that's what
Okay. And this is 1 minus H00, which if I expand becomes 1 plus H00. In any case, I'm not even using that corrections anyway in this derivation. Oh, actually, I'm gonna use it next. Very simple. Any other questions? Okay, then we can, one thing that we can, of course, can be done I haven't done it. It's asked the same question for the relativistic or ultra-relativistic particle, which has to behave the same as light, as massless field, a massless particle. And then we can ask what would be the bending of light by sun. So we just need to take, given that we identified, well, given that we learned what is this proportionality coefficient here, we can determine what is the field of sun and then ask what is the motion of a relativistic particle in the field of sun. So the usual scattering, the small angular scattering problem. So it's essentially the same equation, but now considering an ultra-relativistic particle. This is one of your exercises. It's a very important problem. Okay. Now, one other thing that we can do. Question? No. Okay, so this is the question of light bending. So as you will discover in the homework, light actually bends in a spin 2 gravity, unlike dilaton gravity, in which light decoupled would go in the straight line. In here, light bends, and you can calculate what would be this angle theta. And this has been, of course, checked experimentally with high precision, and it agrees with the experiment. Now, what else can we ask? We can ask about gravitational redshift. So remember when we talked about the scalar gravity, we said that the clocks that live inside the gravitational field, they work slower compared to the ones that live in a shallower potential. So we can ask the same question here. Using essentially the same trick of going to a different set of coordinates in terms of which the clocks work at the same rate as if there was no gravitational field. So remember, the idea was that if I have good clocks, they work based on some microscopic mechanism. If I have a very long wavelength field that is coupled in, I erased it. If I have a long wavelength field that is coupled in this way, well, if I assume that this G mu nu or H mu nu that lives in here has very, very long wavelength variations, but my clocks are having working based on it has some microscopic internal dynamics over which this field is almost constant. We can choose a different coordinate system, x tilde mu, in the following way. So how do we choose them? We choose them in such a way that in terms of those coordinates we have Minkowski at the location of our clock. So it has to be that G mu nu dx mu dx tilde alpha dx mu dx tilde beta is equal to eta alpha beta. in particular, if we have a field like that, there is no 0R component of the field, then we can just focus on the zeros component of this equation. That tells me that G00 times dt tilde, the square should be eta 00, which means that T is equal to eta 00 over G00. So this is 1 plus H00 times T tilde. Or dt is 1 plus H00 d tilde. Outside, there is a square root. Because this was a square, so there will be a square root. Which, if I'm linearizing, it becomes just 1 plus 1 half H00 dt tilde. You agree? Okay. Now, in terms of these tilde coordinates, my clocks work as if they are in Minkowski space. So this T tilde is just 1 over the frequency of the clock that was set at infinity when it was made outside of any gravitational field. So now we can invert this to talk about frequencies. The omega will be 1 minus 1 half H00 times omega 0. Now, if I want to express it in terms of the gravitational potential, it becomes 1 plus phi times omega 0. Now, does it agree with what we had before? Yes. Yeah. Yeah, it does agree. So, if, for instance, if I consider Earth, so if I say phi is Gm minus Gm over R, and talk about someone who is on Earth and compare the frequency of the clock on Earth compared to the one at infinity, then I will get omega on Earth is equal to 1 minus Gm over R times omega infinity. At infinity, my clock works normally.
Here we have a correction with the square root, so
yeah.
If we have a strong phi, our expression will be different than our scalar theory.
Mm-hmm.
They can tell the difference.
Yeah, although we should keep in mind that so far we have only discussed linear theory. Even in the scalar case, we didn't really focus on the nonlinear corrections. So even there you could have some nonlinear corrections.
I see.
It's not that that theory was uniquely fixed, and this is uniquely fixed, and you can match the quadratic, or at the moment at the quadratic level or nonlinear level we have not fixed them. So yeah, I mean it's not determined what the answer is at the moment. Eventually, yes, it will be here as we will see in the next lectures. In the case of spin 2 gravity, the theory becomes uniquely fixed even at nonlinear orders. And then, yeah, there is a definite answer, even if your phi field, your potential becomes large. It's not, even if it is order 1, then you will get some unique answer for the gravitational redshift. Other questions? Okay.
For observers using these tilde coordinates,
Uh-huh.
for them the space looks flat. That's why they measure the eta, alpha, beta metric, or how we should understand.
Yeah, but eventually that would be the interpretation. Although at the moment I have not talked about this space not being flat. So far, this h mu nu was just some field, like Maxwell field that you have. You propagates on flat space.
But at the linear terms, the coordinates only scales or change in this way.
Yeah.
But yeah, okay, so we haven't discussed some more implications on this.
Right. Yeah. At this moment, it's just these are some coordinates. But some different choice of rulers and clocks or times in terms of which this field is absent.
Okay.
And then when this field is absent, we expect that good clocks should work in the same way. Other. But yeah, eventually the interpretation of this new coordinate is that it is a local inertial frame. So these are like free falling, the times and these distances that free falling observers or free falling elevators would measure. Okay, so now let's. I finally want to discuss waves. So let's go back again to this quadratic action that I had here. So the sky is 2, and this was what? It was something like minus 1 over 64 pi g integral d4x d mu h alpha beta d mu h alpha beta plus some other terms. So some quadratic action for h mu nu with a lot of indices. Now again we want to, we have this theory, we have sources, the sources can move, be time dependent, and then as in the case of the dilaton, when the sources move, we will shake this field, h mu nu, and then it satisfies the wave equation. So those changes are going to travel away and be described by gravitational waves. And those waves will carry energy and momentum. And now we have a standard procedure to calculate the energy and momentum that is carried by this gravitational wave. So once I know the action for this field, it's the energy that is carried by the waves of H is fully fixed and determined. What I do is I calculate the stress energy tensor and look at the 0I component that will tell me the energy flux. Right? So remember what we did in the case of dilaton was that we said if we go far away, we're considering sources. They had some frequency omega. We're going far away at distance r, where far meant omega r is much larger than 1. We saw that there, locally what we see is a plane wave that is just moving. And then we took the action for this phi field and asked what is the energy that is carried, or energy flux that is carried by a plane wave. And then given the full configuration of this field over the sphere, the only thing that we had to do was to add up to that energy flux over the whole sphere to get, for instance, the total amount of energy that is going in. So now let's do a similar thing here. Let's ask what is the energy flux that is contained in a plane wave. This time of this field H. Now this field has many indices, but so let's assume that we have a field which is a plane wave H hat mu times e to the I minus I omega t, or minus I omega t minus x. So it's moving along x direction. Now one thing that we can show is that there is a gauge. We can use this diffeomorphism. So remember we had this xi mu and arbitrary function of space-time. We could transform H by d mu xi nu plus d nu xi mu, and that would be the same. They would have the same physical consequence. In particular, this action is invariant on the direction. So what we can do is that there is a choice of this xc mu for which, if I have a plane wave moving in the x direction, then we can do a transformation to a new field using this xi mu, so that the new field h tilde mu will be transverse and traceless and spatial. So what does it mean? Is that this is a tensor, 4x4 tensor. So the way it looks like is that we are talking about a wave that propagates along x direction. There is a choice of xc for which I have a lot of zeros here. Times e to the minus omega t minus x. So in other words, h tilde y is equal to minus h tilde zc equals h plus, and h yc equals h zy equals h cross. I'll give the explicit form of this xc in the notes.
is a gauge choice or what?
Yeah. So again, very similar to Maxwell's theory. You can, if you consider a plane wave in Maxwell's theory, so you have some a mu which is given in terms of, you can imagine a mu given by some a mu hat, some vector times e to the minus I omega t minus x. Right? In Maxwell's theory, what we show is that using the U1 gauge symmetry, we can make this a mu hat to be a spatial and transverse, right? We only have two polarizations corresponding to, so since this goes along x direction, we can choose a gauge epsilon so that in the new gauge, we only have a so how do I write here? I write a mu is 0, 0, some a hat y and a hat z times e to the minus I omega t minus x. Or maybe some other, let me just give them different names. What do I call them? Let's call them, I don't know, B, by, BC. So there is a choice in which I will get, if I have an electromagnetic wave that moves in x direction, there is a choice of gauge for which I only have y and z components of this electromagnetic potential. This is essentially the same thing. There is a choice of this xi mu for which I only have these components to be non-zero. So essentially two parameters. This must be satisfactory because we said that we only have two degrees of freedom or two helicities for a massless spin 2 particle, the same as in the massless with any spin. There are only two helicities, and here we are expressing these plane waves in terms of only two free parameters. So these are the two polarizations of the gravitational waves, the cross and the plus polarization. So what they do is that they, if you really think about the way they change in time, in the case of electromagnetic wave, you have a vector. So this vector, if you have an electromagnetic wave that moves in this direction, then you have a vector polarization that goes up and down. Or you can choose circular polarization that go around as you move it. So there are two circular polarization, one that moves this way and the other one that moves the other way. These are the two helicities. Or we can use linear polarizations instead of circular, and then if I'm moving in x direction, there will be two perpendicular linear polarizations. Now, in the case of gravitons, as you see, they always require two perpendicular dimensions. So both the plus and cross dimensions, they live in two perpendicular directions. So essentially what they do is this, if the wave moves in this direction. So they are perpendicular, but they live in two transverse dimensions. Or you could trade these two polarizations with the circular ones. And again, as in the case of a spin, you will get a circular polarization that is clockwise and another one which is counterclockwise. So again, two. except that it's rotating twice faster than this, than the photon. Okay, so any questions?
Yeah. This result comes from the gauge freedom that we have, that the geomorphisms that we can add. So when, I don't remember if I explained why do we have that freedom, but is it because that we need to have two different helicity having particle, which dictates this freedom, which causes this two different waves?
Yes, yeah. In fact, that was what we were discussing before you arrived. Yeah, exactly. That's exactly the reason.
I've seen this picture of electromagnetic, gravitational wave, that if you have a circle, and then like when a gravitational wave passes through this circle, let's say in space-time, the circle is doing like this, or like stretching in one direction or stretching in the other one. So these are the two polarizations. Like if we see a set of space-time points, the gravitational waves make the points to stretch in some directions perpendicular to the wave.
Yeah, yeah.
That's exactly this.
Yeah.
Okay.
Well, you can, I think you are asked in the homework to actually see this effect, because in principle we know everything, right? We know how the point particles are coupled to this background field, so we can see how they move as this wave passes by. Right, we can just use a point particle action or geodesic equation and see how they move as we have this move. Okay, so we have this field that is now looks much simpler than before. And using that we can simplify this action. If we assume that that's the form of our h mu nu field, you have a plane wave that moves in the x direction, then this action becomes much simpler. It becomes just minus 1 over 32 pi g integral d4x dA times h plus squared minus 30 plus dA of h cross. Where by dA I mean now it's really a metric in the tx plane, or in the tx plane, because we consider the field which only depends on t and x but not on y and z. So this is kind of a mixed simplified notation, which is only valid if I consider this plane waves that moves in the line x direction. I did that because now it looks extremely simple. It looks like the action for two scalar fields, for which I can derive the energy momentum tensor and ask what is the energy flux that is contained in the wave. So the energy momentum tensor, I show it by little t, just to not to confuse it with big T or big T that we are calculating from matter action. Yes.
What's the indices of the derivative?
Oh, this little a's, I mean the sum here is restricted to only t and x. So what I really mean here is that for this configuration you have, this is really minus h plus dot squared plus h plus prime squared, and then a similar expression for h cross, where dot means time derivative and prime means x derivative here. Just because all other derivatives vanish on this concept. So now I can calculate the energy flux, which is minus T0 1 or T0 x. Again, I remind you that I changed my notation. So there is the minus sign in many places compared to the not. I try to go through it and fix it, but the older version might have that minus. So this will be the energy flux. So what would it be? I just calculate the energy momentum tensor from this action using as if this is the action for a scalar field, and then the answer is very simple. It's like two copies of our phi field. So I get 1/16 pi g times. So there is a minus sign, and then I get d0 h plus dx h plus, and similarly d0 h cross dx h plus. Now if I use the fact that d0 dx is minus d0 because I'm talking about a wave, then this so this dx h plus becomes minus d0 h plus. So this becomes 1/16 pi g times d0 h plus square plus d0 h cross square. Okay, so assuming that we derive if we relate this asymptotic configuration of the h mu nu field to the motion of the sources, then we can use this equation to calculate how much energy is being emitted in gravitational waves. So the next task would be to do this, to relate h mu nu far away to the sources, to the motion of, to energy momentum tensor of the sources. And again, to do this, we choose we find a good choice of, we find a good gauge choice to simplify the Einstein equation. No, sorry, not Einstein equation. To simplify or linearize the equation for h mu nu. And what is that? So now we want to find, go from some t mu nu or from the sources to h mu nu. So there is a very clever choice of gauge, which is we're kind of similar to the radiation, or I don't know, the Lorentz gauge that you have in electromagnetism. When we write d mu f mu nu equals j nu, then if we choose d mu a nu equal to 0, then the equations becomes very simple. It becomes box a mu equals j mu. Right, and then when the equation becomes like that, then finding the solutions is easy because we already know what is the Green's function for this differential operator. So once we know the Green's function, we just follow the same strategy as we had before. We can write the field far away in terms of the source, some integral over the sources, some retarded integral relating the field to the value of the source at some earlier time. So there is a very similar choice of gauge in the case of H mu nu field, and that is if we define this new combination H psi mu nu, which is H mu nu minus 1/2 eta mu nu H alpha alpha. And then if I impose the condition that the mu of psi mu nu is equal to 0, then the equation of motion for psi becomes just a box psi mu nu is equal to let's remember what was the coefficient is I think it's minus 30 minus 16 pi g t mu nu. But this psi is this, right? This just this combination of H mu nu. And now the answer to this we can immediately write. If we go far away, then or psi mu nu is just well, this is like having how many, like 10 copies of the Dilaton equation that we wrote before. For every index mu nu we have one equation. Every one of them has the same solution as before. So psi mu nu becomes 4g over r times integral d3 r prime times t mu nu of t minus r prime and r prime. So this is the solution in the wave zone when omega r is much larger than 1. So I took out the 1 over r factor as before. So I'm implicitly assuming that these sources have some characteristic frequency omega. And then we are basically done. There's only one more trick. And then we should go upstairs now. Well, I don't know, I can tell you about the trick or I can leave it to you to read it, whatever you prefer. Who wants to, or maybe let's do this, we finish and then anyone who wants to stay, let's do it, anyone who wants to go. No one wants to go. Okay. It just takes hopefully 5 minutes. So, in particular, we are interested in the components of this psi which are spatials, because far away we saw that we can choose a gauge in which only the H mu nu becomes like that, and similarly, and it is traceless, and therefore psi mu nu becomes like that too, becomes just a spatial. So in particular, we are interested in the in the spatial, the integral of the spatial components of the stress energy tensor over the source. So there is a trick to write this in terms of the quadrupole moment, or some time derivative of the second moment of this t00. And the trick is the following. There's nothing very, I don't know, it's just a trick. So this I can write as d3 r prime times dk of ri tjk. But remember that spatial indices can be raised and lower without any minus sign, because we are in mostly plus segments. So I can write this as this plus ri d0 of t0j.
And we still use to raise and lower eta mu, not j mu.
Yes.
Still working in the linear order of h. That's right.
Yeah, so essentially I'm ignoring h. Remember, this t for us was the zeroth order t mu and mu. So it satisfies the zeroth order conservation law, which does not include h. So this integral can be written like that using the conservation law. The fact that t0 t0j plus tkj is equal to 0. Do you have a class at 4? Yeah. Okay, we are done in 2 minutes. So this can be written as well, this is a total derivative and our source is compact, so this doesn't matter, it reduces to boundary term which vanishes. This then can be written as d0 of d3 r prime ri. So I use the same trick as before, right? dk rj t0k, and then the plus ri rj d0 of t00. Now this first time I can do an integration by parts. It gives me minus integral, let me write the integral here. In the first time I get minus d0 of, so if I do by parts, k and r become the same. So I get d0 of rj t0i, and then in the second term I have ri rj d0 squared t00. But this d0 acts on the whole thing. And then here d0 of t0i can be written as r and plus rj dk of tik, and then I can do an integration by parts that sets j and k to be the same, so then it becomes minus tij. So I take it to the other side of the equation, it gives me a factor of 2. At the end of the day, what I get is that integral d3 r prime tij is equal to 1/2 d0 squared and integral d3 r prime ri rj t00. And then this quantity can be related to the quadrupole moment by subtracting the trace and noticing that here we only care about the traceless part, because asymptotically we choose a gauge asymptotically to make this h traceless. So in this way, our plus and cross polarizations become related to just the quadrupole moment. So there is a factor of 3 here. So one gets 4G over 3R Q y minus QCC double dot. And then for the H cross one get 4G over 3R Q by C double. So once we have this, then we can plug it into our equation for the energy flux and calculate the total energy that is, or total power that we get. One thing that to notice here is that since we were dealing with the spin 2 field, then our expansion already starts at something that we call, remember we had multiple expansion, which was an expansion in powers of omega times r. Now here we see that this d0 squared is a factor of omega squared, and this r is, but these are r prime. These r prime squares are just size of, they correspond to the size of the system. So already, if we assume that the system is non-relativistic, this term already starts from order v squared. There is no zeroth order in v contribution. In a sense, there is no monopole and there is no dipole. The whole thing starts from quadrupole in quadrupole expansion. And then one can truncate the expansion already here and derive the famous quadrupole formula for the total emitted power, which is G over 45. So in the case of a scalar, it was G over 270. Here it is because of these polarization vectors, the overall coefficient will be different. But the general form of the equation is very similar. So one gets the famous quadrupole formula for the total emitted power. Okay, so I guess next week we can either review this again or you ask me if you couldn't follow the algebra. But at the end of the day, I think the logic should, I hope the logic is kind of clear what we are doing. And even if you cannot derive this formula without looking at the notes or the book, this final formula is very similar to what we had for the dilaton waves, in the case when monopole and dipole vanish. And this is something to keep in mind and have, because that is, it has very important application. There are many systems which are non-relativistic, and this formula gives a very good description, a very good approximation to the amount of energy that these systems are losing through the emission of the gravitational wave.